saw how to view log files. So today we're going to see what are counters, how to determine the number of reducers for a job, and how to reuse objects, job objects, how to create map-only MapReduce jobs, and how to use counters and map-only jobs. Okay, so counters provide a way for mappers or reducers to pass aggregate values back to the driver after the job has completed. Um, their values are visible from job tracker web UI, and it is reported on the console when the job ends. Now, and these counters are nothing but by way of counters, mappers and reducer communicate to the job tracker at each and every phase. So at each and every phase, whatever it has read, it's going to communicate a value to the job tracker. Um, once a map and reduce once the program has run successfully. Uh, Once a map and reduce phase has run successfully, we will see the MapReduce this counters. I'll show you the counters in the console. I have run previously one job, so I'll show you how the counter looks like. The counter base is a very basic. It has a name and a value. The value can be incremented within the code. Counters are collected into groups. So we have various groups, right from reading a file when the mapper initiated, the output of mapper came, the intermediate value, the shuffle value, and after that, during the reduce phase, what the output of the reducer when it is returning to the reducer. So all these counters are written in the group. So we have a group and then counter and the value. For example, so this is a program which we ran last time, and if we click here towards the left hand side, we'll see the job overview, counters, configuration, and map task. So if you click on counters, so we will see this counter for job number, job ID. We'll see this. So we have this first column as counter group and the counters. So we have like uh, for each and every task it has done, we have a counter. So number of bytes read in the reduced phase in the and total number of bytes. So all these are nothing but counters. Okay. So these values are passed by the mapper and reducer back to the job tracker. Over here I'm running in Hadoop 2. So these are sent to the application master. These counters are sent to the application master. Okay. So we have when the file has read during total job counters, MapReduce during the MapReduce, during the combining, and any errors when the byte was read during return phase. These are counters. Okay. Group of counters called.
Mohammed,
Yeah.
are these internal to the Hadoop, or these are configurable? I don't think these are all internal to Hadoop, right?
Yeah, these are internal to Hadoop. So these are not configurable, but we have to know about counters
Yeah,
for writing MapReduce programs. We require this. Okay.
yeah, yeah.
Counters are collected into groups. Within the group, each counter has a name. We have a counter group and the counters, and within the counters we have the name and the map and reduce and total. So which one was initiated by map, which one was done by reduce, and what's the total value. So we can see all these in the counters. For example, we have the name type A, type B, type C. Appropriate counter will be incremented as each record is read in the mapper. Okay, so we have seen here for um, the file has been read, we have a counter. If the file has been written, then we have again counter. So all these operations are we have, it's a way of tracking the things. So again, counter provides a way for mapper or reducer to pass aggregate values back to the driver after the job has been completed, and we can see this even in the job tracker web UI. Once a once the task has been completed, we see them in the console, and then we'll see this in the job trackers web UI. Counters can be set and incremented via this method: context.get counter group command name increment by amount. Example: see, we have this record type A, and whenever it has passed through this counter, we're going to get this value 1. It's going to increment this value. Okay, so we can set counters here to keep a track aware of what our mappers and reducers when they have read this counters, when they have read this record. All this it's just to keep a track of it here. uh, to retrieve the counters in the driver code after the job has completed, we use this following code. So we say long type A records and job.get counters, find record of A and get the value. Okay, so by this way we are going to retrieve the value for each counter. So we are retrieving the counters for here. We are retrieving the counters for record type A, record type B. Both the values we are getting. Both the counter values we are retrieving here. During the MapReduce job, when the MapReduce is running, we can view these counters in the web UI, but we should not uh, see those counters and get excited, because these values will be changing, and during the execution these values can be changing. Let's say a map phase has read the files, but that map phase is slow and it has been uh, failed. Then again a new mapper will be initiated, and that mapper is so the counter will be varying. So during the job is running, when the job is running, we cannot trust the counter's value. So once the counter has been once the job has been completed, then we can see the counter's value. Okay. Determining the optimal number of reducers for our job. So how many reducers do we need? So this is one of the important factors considering when we are creating. So the number of reducers has to be specified by us. So the default reducer, if you do not specify, is a single reducer. With single reducers, all the task of receiving all the keys in a sorted adder is that burden, that all the keys will be sent to the single reducer, and this single reducer is responsible to aggregate all the values. So depending on us, when to use single reducer, when to use multiple reducer, we define. Sometimes it is advantageous to use single reducer. If the output has to be in a completely sorted order, we can use a single reducer. It can cause problems when we have large amount of intermediate data. So that case we can have more number of reducers, and it depends on the kind of output also we want. If we want different outputs, then we can choose different outputs. Let's say for example the same word count program which we ran, if we need only 2 letters or 3 letter words, then only those output we need, then we can use one reducer for that. And we want to say we want 10 or 11 letter words, we can use another reducer for that. So we can use two reducers, and these two reducers we can configure in such a way that these two has to write in two different outputs. We can write the output in two different files, we can say it. So we'll get two reducers writing in two files. We can configure this way. So the number of reducers, we don't have any fixed criteria. It always depends on us, the kind of problem we are trying to solve, and the kind of output we are looking for. So based on that, we choose the number of reducers. Typically, if the intermediate data is large, we have more than one reducers to take care of it, to do the aggregation value. So where do we use single reducer? If a job needs the output of a file where all keys are listed in sorted order, a single reducer must be used. Okay, let's say we have patient's file name, and we want the this record to be sorted out based on the drugs which they have bought, and we can choose that in the sorted order, drugs in the sorted order. I will all in such sorted order, we can get that output. So for that, we can use a single reducer, because the intermediate data which is sent to the reducer will be in sorted order. So the same way, it will be sent out. The values will be aggregated for each keys, and we are going to get the new key value pair. We can use total order partitioner can be used. Um, Externally generated file which contains information about the intermediate key distribution. You can use this also, the total order partitioner. Partitioner data partitions data such that all the keys which go to the first reducer are smaller than any which go to the second one, etc. Second, and then like that we can configure this. We can use custom partitioner to specify which keys has to go to which reducer, and this way that reducer will have multiple outputs. And then we can either write it in this way that each reducer has to write the output in a different file, or all the reducers have to write in a single output file. We can in a list in a sorted order we can write it out. So since we want it a single file and in sorted order, we can use multiple reducers here, and then configure them to write in a one single output in a sorted order. Okay. We Jobs which require fixed number of reducers. Now, if you want the job to output one file per day of the week, then we are going to use a fixed number of reducers. Now, let's say we have a report and we want to know the stock. Let's say we have a company and we want to know the stock after each and every day, what is the stock report. So then we can configure that each and every day it has to write the output. This Mapreduce program, we can write each and every day it has to write the output based on the weekdays. And we can use 7 reducers here. Key will be the weekday, and the value will be the total stock of each day. So we will have 7 reducers and 7 values we'll have. So this way we can use multiple reducers, and we can have a fixed number of reducers here. The partitioner will be written which sends one key to each reducer. So we can specify this way. Now the partitioner has to send each day of the week to only one particular reducer, and that will be performed here. Jobs which require variable number of reducers, which we do not know now. So now how to specify that? It's usually uh, we give a guess. What we do is when we write a MapReduce program, we're going to test it out in a small set of data, and based on that result, we take a guess. So this many number of reducers could yield optimal result, um, and that way we choose the number of reducers. Uh, we we usually make a guess here. We don't have any exact method to choose the number of reducers. So sometimes we need to consider the clusters, and in the cluster, how many number of data nodes are there, and how many number of reducers can be available in the cluster. We need to take into that consideration. Otherwise, what we'll do, we can just run reducer multiple times to get the aggregate values. If let's say we have a cluster is limited and we have one a fixed number of reducers, but we have noted that by this number of reducers, the output is slow. So what we can do, uh, we can use a second wave of the reducers. Meaning once we have second phase, one phase of reducers will complete the output return, and then we can have another phase of reducer. So um, this will actually a better utilization of the cluster here. But here again, it could increase the amount of time spent on the reduce phase. So this is something we decide. um, this is something again we take a guess how to increase the number of reducers. uh, we can increase the reducer and see if if it helps. Otherwise, second way of reducers to do our computation. So this way we do it. So fixed reducer is, so to sum it up, so single reducer is used when we want output in sorted order, and if we have a fixed output, we know that the output has to be this, then we can use fixed number of reducers. Let's say we have two cities and we want to calculate it, the population, population here, who have come from Bangalore. So in Bangalore we want to know who have come from Noida, so who are the native origin people of Noida. Then here we can use a specific number of reducers. So Bangalore people, so one reducer, and Noida people, one reducer. So fixed number of reducers we can choose here. And variable number of reducers, usually we take a guess. What we do, we write a Mapreduce programming and we test it out on a small data set, and depending on the time and the kind of output which we require, we take a guess that this many number of reducers will suffice us. And based on the cluster, we should give the reducer number of reducer. If the number of reducer is limited, then we can do a second wave of, we can send a second wave, like more like first phase, second phase. In the second phase of reducer, we can have two phases of reducer we can have, where the output will be written in a single file. We can set it this way. Reusing objects. um, it is good practice for us to reuse objects. That way we have better code. Okay, in the same word count program, here each time we call this map method, we are using this text object and a new iterable object. So but we can make use of the same object to make our code better. So here we are creating the object for our key and value outside of our map method, and then making use of the same objects here. Within the map method, populate the objects and write them out. How do we take care of serializing the object data? So it's perfectly safe to reuse the same objects here. This way we can reuse the object which we have created here. So whenever we Hadoop reuses objects all the time, so each time the reducer is passed a new value, the same object is reused. So we have to be careful when to use object. This could lead to some problem into our reducer. Okay. Um, so when to use map only MapReduce jobs? There are many types of jobs where only mapper is needed. For example, processing image, file format conversion, input data sampling, and for ETL jobs, we are using only mappers. While taking HDFS, I have told about distcp. Distcp is one of the commands in HDFS which is used to copy data between two Hadoop clusters. If you have two Hadoop clusters and you want to copy the data between them, so you are using distcp. So distcp internally uses MapReduce job, and here we are only using mapper to make a copy from one cluster to another cluster. Okay, and in file format conversion, to converting from one format to another format, we are using only mapper. And input data sampling, while sampling this input data, we are using only map phase and not the reduce phase. Okay, even during ETL operation, we are using only map phase here. To create a map only job, set the number of reducers to 0 in our program, in our driver program, and then we can execute them. So call the job.setOutput key class and job.setOutput value class method to specify the output classes, and uh, job.setMapOutput key class and job.setOutput value class methods. We are calling these two methods to set uh, to set the number of reduce. So anything we write in the contextual write method will be returned to HDFS rather than written as an intermediate data. So one file per mapper will be written. So it is mainly useful for when we are converting file format from one format to another format. You can use this, or during ETL operation, or during parallel copying, or during data archiving. When we are archiving the data, so we are using only map phase. So now let's see about input data and output data. What we're going to learn today is how to write custom writable and writable comparable implementation. Uh, how to write sequence files and Avro data files. How to implement custom input formats and output formats, and we're going to see about file compressions. So the input to mappers is from. So I have already explained, we have input blocks. So each block is for a small chunks called as input splits, called as input splits, and each split is nothing. Let's say, for example, if you have a file which contains 10 lines, and the input split, this is nothing but a block, and this is further broken down into line by line. This is called, each line will be called as an input split, and the record reader is responsible to send the offset value for this line, whereas the starting point and the ending point of this line, and this is the key. This offset is the key. This offset is the key, and this offset is the key. This key is this key along with the whole sentence is sent as a key and value pair to the mapper. The record reader is responsible for sending the and sending the offset value to the to the mapper. The output of mapper is going to be an intermediate key value pair, and that is again shuffled and sorted, and then that shuffled and sorted intermediate data is sent to the reducer. The reducer is going to receive uh, a key and all the unique values for that key. So key and a value list pair is going to be sent to the reducer, where the values are aggregated, and we're going to get a new key value pair, and this new key value pair is written in the output. This new key value pair is written via the record writer. Record writer here is responsible to write the each reducer's output on the output file. So the data types in Hadoop are writable, writable comparable, int writable, long writable, and text. So writable is an interface which extends writable comparable, and int writable, long writable, and text writable extends writable comparable. So writable defines serialization or deserialization protocol. Every data type in Hadoop is writable. Writable comparable defines a sort order. All keys must be of writable comparable, and int writable, text writable. Concrete class, it defines the concrete classes for different data types. Okay, we have seen the Mapreduce program. We are going to use int writable, long writable, and text. We are going to use these as the input and the output of mapper and reducer. Okay, so Hadoop uses built-in data types, and these built-in data types are available in the box classes. They contain a single piece of data. So text, int writable, long writable, float writable. These are the few of the uh, um, Hadoop. These are a few of the data types which are available in the box classes. Um, Writable defines the wire transfer format. Okay, writable is going to serialize your data, and then is also used for deserializing the data. Let's say we have a tuple of a comma b. Okay, tuple is nothing but a row. So a row of a comma b we have. We would we would artificially construct it by saying text t is equal to new text of a plus comma b, and we are defining the string of array to split this line by the comma. Okay, so this way we are going to use a writable, and we have seen this code in our program also, where we have implemented this. We are going to see, we have seen this in the mapper program. We have seen this, it's going to split here. We have seen, see, this is the code here. Each string is, we are getting the each line, and each line is split based on the commas. So okay, so based on the commas each line is split, and then we are taking the um, elements 2 and 4 of the line. Each element 2 and 4 we are taking, and then writing the output here. So this is this is actually complex way. So we can write this way, this will work, but this is not recommended, and this will create problematic, because as A or B contain commas. If A or B contain commas, then it's going to split them. If you want only the words to be split, we are going to use this. Most of the time we try to avoid this way. Okay, this one. doesn't work for binary objects. So when it doesn't work for binary objects, so we write our own writable objects. So the writable interface consists of public. Yeah, this is the writable interface. So you void read files, data input of in, and void write of data output of out. We want to say this. So read fields and write methods will define how our custom objects will be serialized and deserialized by Hadoop. The data input and data output classes supported are boolean, byte, character, double, float, int, long, string. These are uh, the data input and output classes supported by Hadoop by the writable interface specifically. So how a custom writable interface looks like? So we are writing a data here. It's going to read the fields and read it in month, day, and year. In this format, we are going to read the input. And so the read field is going to get input of input file, and that input text. Let's say we are sending the input to this writable interface as month, day, and year. Um, that input is further split. So we are reading month, day, and year, and the same thing we are writing it out. So as month, day, and year here. This is an int, and we are overriding the APIs here to read the outputs in this format. So how binary objects are read and written. So if we are having a byte, we are going to use a byte arrays. So we're going to serialize the object to byte array, write the byte count and the byte array, and the same way we're going to read. So read the byte count and create a byte array of proper size. Read the byte array and deserialize the object. Writable comparable is a subinterface in Writable, and it must implement these methods compared to hash code and equals methods. It must implement this, and all keys in Mapreduce must be writable comparable. So this is a must. All keys in Mapreduce must be a writable comparable, uh, or it has to be of writable comparable interface. It has to be of type writable comparable. Okay, so our writable comparable method. We are in this course says how to make a sample objects of writable comparable. So we are taking a write data. We're defining a class which implements writable comparable, and in defining the arguments as data writable, and then passing the arguments as month, day, and year. Okay, we are we are We are using the read field and the read field method, and this is the write method. We are going to read the month, day, and year, which we saw these examples previously. Here in the booleans, we are overriding equals method, and uh, we are defining here the logic here. If this year is equal to the other year and this month is equal to the other month, then this day is equal to other day, then return false. Okay. If it is equal, it will return true, and if it is not equal, then it will return false here. Okay. So here we are comparing the year, this dot year, and the other year, month, and the day. So if it is equal, it is going to return the value. Otherwise, it's going to return for. If it is for it's not equal, then it's going to return false. Here, it's going to return three values. If it is -1, if the date is earlier; 0 if it is equal; and 1 if the date is higher. If the year is not equal, then it's going to return -1. If else, it's going to first check the year, and here it's going to check the month and the day. If the year is not equal, then it's going to return the year is -1, and if the month is not equal, it's going to return -1, and the day is the same -1. Otherwise, it's going to return equals means it's going to return 0, or if it is higher, then it's going to return 1 value here. And if we are defining the hash code, this int seed is equal to 163. We are giving an arbitrary seed value, and multiplying to the return, multiplying the values to the year, day, and returning that value. We are generating a random ID uh, for this object here. For the key, we are generating a random ID here. Okay. Using custom types in our Mapreduce job. Now, how to define custom key value types here? So to define custom key values, we are going to use the we are going to set class and the reducer class. This way, we're going to define set mapper output key class and set map output value class. So by defining these in our driver code, we're going to see the input format and custom data type, custom output we're going to get. Custom key value pairs, we can define this. Sequence files are files containing binary encoded key value pairs. So these binary encoded key value pairs work naturally with Hadoop data types. So the default data types which we have defined here, int, long writable text, all those data types, it naturally works with them. And sequence files include metadata which identifies the data type of the key value. Okay. So there are three types of files in one. So uncompressed, record compressed, and block compressed. We're going to pass these three types of data for our Mapreduce job. These are often used in our Mapreduce program, and the output of job is used when we have the output of one job used as an input of another job. So then we are going to define the sequence file input format. Sequence file input format and sequence file output format we are going to define, and then we are going to get the output of one job will be sent as an input to another MapReduce job. So how to access sequence files from our code? So first we're going to create a configuration object, and then we're going to read the sequence file. This sequence file path we are going to specify in the command line, and from the command line we are passing the arguments here, and then we are going to generate a key and a key class we are going to define, and the value we are defining the key we are defining of text type, and then we are passing the keys here and the values we are passing, and then we are writing the logic how to make use of this key value pair in our mapper code or in a reducer code. We are passing those here. So we are writing. We can use this here. We can call our mapper method or reducer method in this line. Sequence files are very useful, but have some, because most of the time we're using the native Java API, and since Hadoop allows streaming of Hadoop, then it cannot. This sequence file sometimes may work or may not work. So the definition of a key value object changes and the file becomes unreadable. Um, Hadoop provides streaming API wherein we can write our MapReduce program, mapper class and reducer class in any of our language like Perl, Python, Ruby, and then we are writing the driver code in Java, and from there, from the driver code, we are calling this mapper and reducer method. Um, the input and the output will be sent to this mapper and reducer method. The mapper logic will be performed, and once once the mapper or reducer has written the output, it will be passed back to the driver code, and from the driver it will be displayed to us. Okay, so sequence files are not good when we are writing a MapReduce program in another language. So streaming is not possible with sequence files. So the alternative for that is Avro. Avro is a serialization format which became popular alternative sequence files. That was a again project created by Doug Cutting, who's the creator of Hadoop. So it's a self-describing file format. The schema for the data is included in the file itself. It's very compact file format. It is portable across multiple languages, and it is compatible with Hadoop. So via the Avro mapper and Avro reducer class, it is compatible here. Implementing custom input formats and output formats. The same way, the input format, what is an input format? The input format consists of input splits and record reader. Um, the input split is nothing but small chunks of the block, and that block is sent to the record reader. Record reader which determines where's the starting and ending of this small piece, and that is sent as a key value pair to the mapper. Mapper generates an intermediate key value pairs, and that will be sent to the reducer. So some of the most common input formats are text input formats, key value text input formats, sequence file input formats, and other input formats are n-line input format. Every n lines of input file is treated as a separate input split. That is, here we are defining what is the input split here. We can say that first 10 line is an input split and send it. For our word count program, we can say first 10 line as input split and then send it to our mapper class, and we can configure the driver code. We're going to configure, if you're using n-line input format, so we're going to define these two lines in Hadoop in the driver program. If you have multiple file input format, we can define it's an abstract class that merges the use of multiple files in a single task. If you have multiple files, then normal way of defining them is using the tool runner method and defining the -d flag and then saying these are the files, multiple files. So we can read multiple files, or we can use this a multiple file input format to send multiple files as a single task. And we have to supply a get record reader method. We have to implement that. We have to supply this method to read these multiple files. So, or a file-based input format inherits file input format. A file input format computes input split based on the size of each file in bytes. So this is internal, so we will not be able to define this. HDFS block size is used as an upper bound for input split size. Lower bound can be specified in driver code. So we can say where is the starting point, but the ending point is usually the upper bound of a block size. Um, the input split typically correlates into to an HDFS blocks. So the number of mappers will be equal to the number of HDFS blocks of our input data to be processed, and each block is further divided into splits. Number of splits is equals to the number of um, mapper phase. The input split is actually defined by the size. Okay? Yes, defining the input split by the size. You're not defining input split by there's no any particular way of that this line, we don't have any lines like that, but we are defining input splits by the size. Since we are defining input splits by the size, it does not respect the boundaries, record boundaries. Okay, more meaning, so this is what I mean to say. So it does not respect any boundaries. It could be uh, anything. So we have this as a one input split and this as another input split, from here to here as one input split, and from here to here another input split. So it is actually based on the size and it is not based on any particular value or line. In the program we define that input. So we know that the block size will be 64 MB, and input split is defined by a particular size, and this size lower bound is defined by us. We have a control over the lower bound, but the upper bound is usually 64 MB or 128 MB, which we set that by default it will be 64 MB. And this input split is actually the size of each chunk in the block, and that is defined by the size here. So it will not respect the any boundary record boundaries. So if it satisfies this particular size, there it's going to make a cut, and then a new input split will begin. Don't worry about the mapping of these two. The mapping is taken care by the framework itself. So this definitive size is going to cut and then it's going to read it. So input splits are handled by the record reader, and the record reader specified by the path. It says where the starting position of the offset and the length of the offset. So this is what record reader is going to specify, and this specification is going to be sent as a key value pair to the mapper phase. It ensures each key value pair is processed No key value pair is processed more than once. This record reader's job is to ensure each key value pair is processed. No record reader more than once, and each key value pairs are split across the input splits. So the record reader here is responsible to say what is the starting position and the ending position of the line. Okay, the length of this line and all these detail, all the three details. What's the length of the line? What's the starting point? What's the ending point? These three details is the record reader is responsible, and this is sent as a key, and the whole sentence as a value to the mapper face. So writing custom input formats uh, using the file input format. Using the file input format as a starting point, we are going to extend it. We are going to write our own record reader. We're going to write our own record reader and then override the get record reader method in the file input format. And then override is splittable. If we do not want to want input files to be split, we're not going to mention it. Yeah, uh, override is splittable if we do not want to write input files. If we do not want input files to be split, method is passed to each file name and then passed. Um, it return false for non-splittable files. So the role of the output format. The output format is responsible to the output format consists of record writer, and the record writer is responsible to write the output of each reduce space into the output file. Okay, the output file we define where the path of the output file is. The record reader will write the output of reducers to this output file. Uh, it is similar to output format is similar to the input format class. Custom output formats must provide a record writer implementation similar to the input format class what we defined. It's similar here. File compressions. We have few issues with file compressions. We're going to see what are those issues. Hadoop understands almost all the variety of file compression. If we can say we can input a file, compressed file, and ask Hadoop to perform MapReduce operation, and it will perform the MapReduce operation gladly. MapReduce accepts any kind of data, structured data, unstructured data, semi-structured data. All these three kinds of data it will accept, and it will perform the MapReduce operation. If a compressed file is included as a one of the file to be processed, Hadoop will automatically decompress it and then pass the decompressed contents to the mapper. So as a developer, we do not have to worry about decompressing the file. Gzip is not splittable file format. So Gzip can only be decompressed by starting at the beginning of the file and continuing to the end. So we cannot start decompressing the file part of the way through it. So Gzip is not compatible with Hadoop. So instead of gzip, we recommend to use other compression formats. If the MapReduce framework receives a non-splittable file like a gzip file, it passes the entire file into a single mapper, and this can result in one mapper running for a longer time than the others, and it is dealing with the entire file while others are dealing with smaller portions of file. So this could be this could result to speculative execution, and even though it doesn't provide any benefits, because even that second mapper could be running for a long time. So that is why gzip is not good with MapReduce. So we don't recommend to send gzip file. So instead of gzip,
Mohammed,
yeah.
yeah, sure, yeah. Say that input split is equal to the size of HDFS block, but in this case, the file can be more than the HDFS block?
Input split is not equal to size of HDFS blocks. Okay, the input split is actually nothing but, so we have block size. Block size is 64 MB. The
Mhm.
input split, we are going to define the size of each input split. Okay, and based on this size, it's going to be smaller than the block size. The lower bound is going to be always smaller than the block size, and based on this input split size, the blocks will be further divided into smaller pieces, and this is then along with the offset value, which is determined by the record reader. This record, this offset value and the input split, the whole input split as a value is going to be set as the key value paired to the mapper face. Okay,
Mhm.
so what I'm trying to tell you is the size of a block is different, the input split size is different.
Okay, okay.
Hope you understand. Yeah.
Yeah, I
Any
got it.
okay. Okay, but when you're sending gzip file, it is going to take it as a one single file and process the entire file in a single mapper. A single mapper is going to be responsible to process the whole file and then send the output. Since we have a single mapper and it could be taking long time, so a speculative execution could occur, and that could result in longer processing of the whole Mapreduce job. So instead of gzip, we recommend LZO. So one of the splittable format is the LZO. Splittable compression format is LZO. So because of licensing restriction, you can LZO is cannot be LZO cannot be shipped with Hadoop. But it's easy to use, and we can find more information about LZO in the GitHub. To use LZO splittable format, we first index the file, and this file is contains information about how to break the LZO file into splits that can be decompressed and then sent further. So accessing this splittable LZO file is very simple. We're going to specify the LZO text input format class, and in the streaming job specify the input format as .com.hadoop.mapred.deprecated LZO text input format on the command line. We're going to specify these in case of streaming jobs. Okay, we're going to specify this in case of streaming jobs only, and then being submitting to the Hadoop cluster. Uh, Nappy Codec is a new compression codec. It's developed by Google and it's very fast. So Snappy does not compress sequence files and produces a file with .snappy extension. Um, Rather than LZO, we use Snappy. So we recommend, if you have Snappy compressed files, it will be easily decoded and compressed, and then that will be splitted, and then it submit to the cluster. When you submit the cluster, it will be decompressed easily and splitted, and then further it will be done as a MapReduce job. um, Compressing output sequence files with Snappy is also very easy. So specify the output compression in the job object and specify block or record compression. Block compression is recommended for Snappy codec. um, so example for Snappy codec is as below. So we're going to import this library. We're going to import the Snappy codec library, and then here we're going to specify job.set output format class equals to sequence file output format dot class, and file output format class we're going to specify job.true, and then we're going to write the output as Snappy codec. Okay. So here's where we are going to get the output. Set output compress class, the job, the output of the MapReduce program, and we're going to specify set it as a Snappy Codec class. So we're going to see some of the common Mapreduce algorithms. Um, so we're going to learn how to sort and search large data set, how to perform secondary index, how to index data. We're going to learn about inverse document frequency, how to compute term frequency and inverse document frequency, how to calculate word co-occurrence. So MapReduce job is short in terms of lines of code. In production, it could be larger depending on the business requirement. It could go to up to 200 to 300 codes, 300 lines of code. It again depends on the business logic and the kind of problem you're trying to solve. Uh, Usually, we use multiple of small MapReduce job to perform a single workflow. In a single workflow to perform our task, and we'll see that we'll see an example for that. Um, Many of our MapReduce job is going to be very similar in code. Excuse me. We're going to see some of the commonly used MapReduce algorithms. Um, these algorithms are uh, frequently used basis on the complexity of the MapReduce jobs. MapReduce is very well suited for to sort large data set. Keys are passed to the reducer in the sorted order. Suppose the file Suppose the file to be sorted contains lines with a single value. Mapper is merely the identity function for the value. So mapper is going to identity function is nothing but each key, each value is going to be only the each value and the key is going to be signed. Okay. So reducer, if you want reducer as the identity function, we can use the same way. See here, the input to mapper is going to be a key value, and we're going to only going to get value, and this is the identity function. The same way in the we're going to use reducer as an identity function, wherein the key value pair, if you pass, the only the key is sent out in sorted order. So we can use a MapReduce program to sort large data sets. Um, Sorting becomes very easy if we have a single reducer. As we have seen, if we say have only one single reducer, then we get the output in a sorted order. So we have single reducers. For multiple reducers, we need to choose the partitioning function such that if the value k2 is a value of k1 is um, if the value of key is less than, we have two keys k1 and k2. If the partition is happening at K1, then we are going to use one reducer. If the partition is happening at K2, then we are going to use another reducer. We can use sorting as a way to test the speed of Hadoop, and this is usually frequently used when when you are increasing the number of data nodes in a cluster. We check this. Um, Mapper and reducers are trivial, meaning this speed test is not that important, but it does give us a good measure of the performance of our cluster. And reducer, mapper and reducer is it's for mapper and reducer is very simple, so it's nothing to act for the mapper and reducer job. So sorting is very fast. uh, we run and time a sort job before and after we add more nodes, so this way we can adjust the speed of our cluster. Assuming the input is a set of files containing lines of text, we can do a searching. The searching is used as input file is a set of files containing number of lines of text. The mapper has been passed a pattern for which to search as a special parameter. Meaning we want, let's say we want to search this particular word in the, and this that as a parameter. We pass that as a parameter to search in these files. Uh, Earlier we have seen how to pass the parameter, so that method we are going to follow here to pass the parameter. The mapper compresses the line against the pattern. If the pattern matches, the mapper outputs line comma the value or file name plus line as the value. If the pattern matches, then the mapper output is going to be line and the value. This is the line if it matches the pattern, or file name plus line as and the value. This way we're going to get the output. If the pattern does not matches, then the mapper will not output anything. Reducer is again is the identity reducer, so just output each intermediate key is going to reduce. Keys are passed to the reducer in a sorted order. The list of values for a particular key is not sorted. The list of keys for a particular key is not in sorted order. Then uh, let's say we have the 2 or 3 different Mapreduce jobs running and we want a sorted output, then we use secondary sort. Job needs to receive the values for a particular key in a sorted order, then we are using secondary sort. We have 2 Mapreduce jobs. Let's say we have 2 Mapreduce jobs and the output of one Mapreduce is not in sorted order, then we are going to use secondary sort and then send that as the input. After the secondary sorting, whatever is the output of that, we're going to send it as an input to a new Mapreduce job. Okay. If reducer emits largest value produced by mapper for each different key, then if a reducer outputs largest value produced by mappers for each different key, then this is our requirement. The reducer should emit largest value produced by the mapper for each different key. Then what we can do is loop through all the values, keeping track of the largest number, and finally emit the largest value, or arrange for values for a given key to be present to the reducer in a sorted descending order, and is to read and emit the first value it is given for a key. So this way we can get the largest value for the mapper has read for each key. We can use comparator classes. Comparator classes are classes that compare objects. We can use that. Custom comparators can be used in secondary sort to compare composite keys, and grouping comparators can be used in secondary sort to ensure that only the natural key is used for partitioning and grouping. We can use these three classes. Okay. To implement secondary sort, the intermediate key should be a composite of the actual key value, and we are going to define a partitioner which partitions just on the natural key. We're going to define a comparator class which sorts on the entire composite key, ensures that the keys are passed to the reducer in desired order, and orders by natural key, and for same natural key, and on the value of the portion of the key. Uh, we are going to define this in the driver code by job.set sort comparator class, and we're going to define the class here, the comparator class we're going to define here. To implement the secondary sort, uh, all the values of the same natural key will go to the same reducer. We know that because that's a job of the partitioner, and we also know that they will be in the order which we desire, and we must ensure that all the values for the same natural key are passed to one call to the reducer. This is also again the job of the partitioner, so we will define that way, and we are going to achieve this by grouping comparator. Define which key or values are passed in a single call to the reducer, and looks at the just natural key and specified in the driver code by this way. Set grouping comparator class, and we're calling the class here comparator class. Example: our task is to find the largest value of the mapper. We know that the output of mapper is going to be a key value pair, and we're going to find out what is the largest value of a key the mapper has sent the output. Okay, we want the reducer to receive the intermediate data for each key in descending numerical order, so we are going to ensure that. So the mapper, we're going to write the mapper class in such a way that the intermediate key is a composite of the natural key and value, and this is going to be the output of mapper. We're going to ensure this way the output of mapper is emitted. So foo hash and 98, that is the value, key and the value and the value. So we're going to pass this way. Uh, and then we're going to write a class that extends writable comparator and sorts on natural key for identical natural keys, sorts on the value portion in descending order. So we're going to override the comparable. We're going to override the it's compare of writable comparable and writable comparable. It's going to receive two arguments of writable comparable type, and we're going to supply a reference to this class in our driver code using set sort comparator class method, and this will result in keys being passed to the reducer in the sorted order. Finally, we write another writable comparator subclass, which just examines the first portion of the key, and again override the compare class, and supply a reference to this class in our driver code using set grouping comparator class method. This will ensure with the same natural key will be sent to the same pass of the reducer, and they are in sorted descending order, and we're going to get the Okay, so we have completed secondary sort. um okay guys, I think um let's stop for now today. Let's stop it here. We'll see the indexing, creating inverted index, all these algorithms and all these methods we'll see in the next class. Okay. Hello.
Sure, Mohammed.
um, Abubakar. Abubakar, how you found the class? I hope you enjoyed the class. Hello. Okay, Kishore, I'll see you tomorrow.
Sure,
Then uh, we will see more of this algorithm, and we'll continue from here tomorrow. Okay.
sure, sure.
Thank you, Kishore.
Thank you. Thanks a lot.